Good morning and welcome to Tech 293 on Thursday, April 8th. The purpose of today's videos is to take the material that we talked about in class on Tuesday about beam bending and flexure testing and apply it to some more real-world applications. This will be really good practice for the next quiz or exam, and it's also really good practice for you for Lab 8 because these are some of the same types of calculations that you'll have to do as you're designing and building your beam for Lab 8 and also writing your lab report for Lab 8. So there are actually two example problem sets for beam bending problems, and you have them both already. They're already in your lab manual. One of them starts on page 87 and goes to page 88 of your lab manual. The other starts on page 89 of your lab manual. What I would strongly recommend that you do is to stop this video and do those problems in those worksheets on page 87, 88, and 89, and then come back to watch this video after you've given it a shot, after you've attempted those problems. I promise you, you will learn a lot more and the material will stick with you a lot longer if you try to solve the problems yourself first and then come back and watch as I explain how to do the problems. If you just follow along with me without having done the problems yourself, the material is probably not going to stick with you and you're probably going to have more problems when you go to do this on the exam. So that's why I strongly recommend you try to do it by yourself and then come back and listen to me explain how to do them. So I'm going to assume that you have paused the video, you've tried to work them out yourself, and now let's go ahead and talk through the example problems, starting with the worksheet on page 87. For the first problem set, starting on page 87, I actually have these on the slides, and for the second example set, I'll do those on pen and paper. So for the first question, on page 87 in the lab manual, we're going to be given the force versus deflection diagram and the geometry of the beam, as well as the support conditions and the loading conditions, how it was loaded. And we want to find the flexural strength. Remember, the flexural strength, aka modulus of rupture, this is the value of stress when it was at its maximum, the maximum value of stress that this beam can support, all right? So here is our force versus deflection plot. Remember, this is not a stress strain diagram. So you can't just say, oh, that's the maximum, I'm gonna read the stress value over there. This is not stress. So that's actually part of the problem, is that we need to calculate this stress right here. That's gonna be the modulus of rupture or flexural strength if we calculate this stress value right there. All right, so that is the question. We want to calculate this flexural strength, and we are given that it is a simply supported beam, and the force is a point load force applied in the middle of the beam. All right, so simply supported beam, point load applied in the middle. So we have an equation for stress for a simply supported beam for a point load in the middle, and this is that equation. Remember, I gave you 8 different equations last time. Actually, I gave you 2 equations for moment of inertia, and then I gave you 4 equations for deflection, depending on the loading and support conditions, and I gave you 4 equations for stress, depending on the loading and support conditions. All right, so this is the equation for stress for a simply supported beam with the force applied in the middle of the beam. All right, so that's the only one like it. That's the only stress equation for a simply supported beam and a point load applied in the middle. So you got to find the right equation to use. That's step 1, I guess. All right, so here's our equation. The question is basically, what's this stress when we are at this point in the test? All right, so we got to plug in numbers. So 1/8 is just a constant. F, what is the force? Okay, well, we can read that from moving over here to the left side. And it's about 15 pounds force. So that's what we're going to plug in for F. L is the length or the span of the beam. And we're given up here, it's only 2 inches. It's a pretty small beam. So L is going to be 2 inches. H is given. That's only 0.125 inches. That's 1/8 of an inch. And I is the moment of inertia. I don't know what that is yet, but I have all the things I need to calculate I. So it looks like what I need to do here, I need to find I, moment of inertia, given these values here. And then I can plug in I to this equation right here, and I can find the stress. So let's do that. Our equation for the moment of inertia for a rectangular or prismatic beam, anything but a cylinder basically, is bh cubed divided by 12. B is the base or the width, and that is ½ an inch. And the height is given up here as 0.125 inches. We cube it, don't forget to do that. And then we divide by 12. And so if you plug that into your calculator, you're going to get 8.138 times 10 to the minus 5 inches to the fourth. That's going to be 0.0000838 inches to the fourth. That's our value of moment of inertia. Now that we know I, we can plug into this equation for stress, because flexural strength is a value of stress. Flexural strength is a value of stress. So we plug into our equation for stress, and we plug in F. That is this value right here, 15 pounds force, times the length or the span, that's 2 inches, times the height of the beam, that was 0.125 inches, and divide by 8 and divide by I. So here's our moment of inertia. Plug all of that into your calculator, and you get a stress value of 5,760 psi. So that is the value of stress when we are at this point in the test. All right, this is the amount of stress in the beam that's going to cause, ultimately going to cause failure to the beam. Now in the next problem, we're going to have the same geometry and everything, but we want to calculate the flexural modulus, E sub B. So once again, we have a simply supported beam with a force applied in the middle, and we need to find the flexural modulus. Note that what the flexural modulus is not is the slope of this curve. Why? Because this is not a stress-strain curve. And in tensile and compressive testing, we could calculate the modulus, the Young's modulus or the elastic modulus in tension or compression, just by taking the slope of this curve, rise over run. But we can't do that here because this is not a stress-strain curve. So we have to find an equation with E sub B in it, and we have to solve for E sub B while remembering that it's only valid in the elastic region of the curve. All right, so those are all some things that we're going to have to deal with here. So the only equations that have E sub B, the flexural modulus, in them are the deflection equations with these right here, solving for the maximum deflection. So we need to find the maximum deflection equation for a simply supported beam with a force applied as a point load in the middle. And if you look in your notes or look in the video from last time, you'll see that the equation for that is the maximum deflection equals 1/48 times FL cubed divided by EI, the flexural rigidity. All right. So we can take that equation and we can rearrange algebraically to solve for E sub B, the flexural modulus. And when you do that, you multiply both sides times E sub B, and you divide both sides by the deflection, and you end up with this equation right here. The flexural modulus equals FL cubed divided by 48 I times the maximum deflection. All right, so now we can use this equation to solve for the flexural modulus. And what we're going to do is we're going to pick a point in the elastic region. So somewhere in this region right here, and we're going to get a relationship between the force and the deflection in the elastic region. So this looks like it's well within the elastic region. Looks like, I would say we start to enter the plastic region, maybe somewhere up about here, thereabouts, when it really starts to curve over some more. So it's more or less linear, I'd say up until about right there. So pick a point in this region, and I'm going to pick right there. So it looks like at this point, when I apply 5 pounds force, I get about 0.05 inches of deflection. So For this equation, I'm going to plug in 5 pounds of force here for F, and I'm going to plug in 0.05 for the deflection, and that is this value right here. So the deflection, this maximum, don't get confused by that. That refers to the maximum deflection point. Where on the beam do you have the maximum deflection? Obviously, by the supports, your deflection is going to be 0 because you're supporting it right there. What this means is that in the middle of the beam, that's where your maximum deflection is. Okay, that's what the maximum deflection means. All right, so for this value of deflection for delta max here, I'm going to plug in 0.05, looks like. All right, so let's go ahead and do that. So we plug in 5 pounds force for our force, and we plug in the span L, and we cube it, and then we take 48, that's a constant. This is the moment of inertia, which we actually calculated already in the previous problem. So I didn't really have to do this, but for clarity, I put it in here. So this, once again, is the base times the height cubed divided by 12. So this whole thing right here is just I, the moment of inertia. And then we multiply that times delta max, which, like I said, was 0.05 inches. And when you solve all of that and you carry through your units and you cancel out your units, then what you end up with is 204,800 psi as the flexural modulus for this material. All right, that is the first two questions on page 87. Now we flip to page 88. And what we're going to do with this is find the deflection of a simply supported shelf with a uniform load across the shelf. So this is very much like this. This is a shelf. This is simply supported because it has a support here and a support here. Never mind the part in the back. Okay, it's not identical to that, but it's pretty similar. So it's a simply supported shelf, support on both sides, and a uniform load, as though we have like a set of encyclopedias where we have basically the same book repeating over and over for a uniform constant force per unit area. All right, uniform load applied across the shelf. And that's what we're trying to solve for, the deflection of the shelf. That's the first part. So let's do that. All right, the first part is to take a minute or two and understand what it's asking, because there are a lot of words here. We're trying to find the deflection of this shelf made of eastern white pine. So we're going to have to probably find the flexural modulus for eastern white pine. And, oh, it actually gives it to us right here. The flexural modulus is 1.36 million psi. And it is supporting a uniform load of 25 pounds force per foot. And the resulting stress is in the elastic region. So this is very nice and convenient. And the problem is telling us, you know what, don't worry, it's in the elastic region. You don't need to check and make sure that it's below the flexural yield stress, because I'm telling you, it's in the elastic region. So you can go ahead and use that flexural modulus, which is valid only in the elastic region. All right, so that's nice. That's nice. That saves us some work here. We're given the dimensions of the part, and we know that it spans 24 inches. All right. So the first thing we're going to have to do is look up the equation for the deflection of a simply supported beam with a uniform load. Right. We're going to have to look up that equation. And one of the things we're going to see in that equation is that we need to find I. Right. We need to find the moment of inertia. So that's probably the first thing we should do, is calculate I, the moment of inertia, and then we can plug that I value into the equation for the deflection. One other thing I'm sure we're going to need for that equation is F. That's the total force. And here we're given the uniform load, 25 pounds per foot, and we're told that the span is 24 inches, but we don't know F. It's pretty simple to find out in this case, but we're going to have to calculate what F is. Once we know F, the total force, and once we know the moment of inertia, then the rest of it we should be able to pretty much just plug straight in. So let's go ahead and do that. Here's our equation for deflection for a simply supported shelf with a uniform load applied to it. And like I said before, we're going to have to find this I. We don't know that yet. And we don't actually know F yet either. But the span is given to us and the flexural modulus is given to us. So once we find that and that, we can plug it in and solve for it. Okay, there's our equation for the moment of inertia. For any type of rectangular beam, that's always the equation that you're going to use. So let's solve for the moment of inertia. Plug in for B, the width. That was given as 4 inches. And the thickness, or the height, should say height. The height of the beam was 0.75 inches. We cube that and divide by 12. And we get the moment of inertia is 0.1406 inches to the 4th. Now we have I up here, but we don't have F yet. But it's pretty simple to calculate because we have a uniform loading of 25 pounds force per foot, and our length or span was given as 24 inches. But to make those units cancel out, you got to convert one or the other. So I'm going to go ahead and convert into, I'm going to convert 24 inches into feet. So for L, I'm going to plug in 2 feet instead of 24 inches. This brings up a good thing, though, a good thing to talk about. You got to be careful of your units, because what if I had plugged in 24 inches right here? Then the answer I would get over here would be 25 pounds force times inches divided by feet. And inches and feet don't cancel out. So you have to look at your units. Don't just plug in numbers and assume the units are going to cancel out. You gotta be a little bit careful when you're plugging in these units. To make these dimensions cancel out, I gotta plug in feet right here. Or I could convert the other one over here to pounds force per inch, but I chose to do it this way. I think it's easier. So for L, they told us it was 24 inches, but I converted to feet. I got 2 feet. Now this foot cancels out with this foot, and I get a total force of 50 pounds force. Now I can just plug everything into this equation right here, which is what this is up here, and plug in 5. That's part of the constant. F was 50 pounds force. L is the span. Now be careful of what units you're going to use here, because down here I know I'm going to plug in E sub B, the flexural modulus, in terms of PSI. What is PSI? Pounds force per square inch. All right, so if I want my units to cancel out and I'm using PSI, then I better put L in inches. Otherwise, they're not going to cancel out. Also, your I, moments of inertia, is in inches to the 4th. So you're using inches down here in the denominator, so you better use inches up here in the numerator so they will cancel out. So here I had to put in 24 inches, not 2 feet, but 24 inches for L, and then we cube it. And then the denominator, we put in 384, that's part of the constant. That is our flexural modulus that was given to us in the problem, and this is the moment of inertia that we calculated right there. So plug all that in and keep track of your units, cancel out your units, and you will find that the deflection in the middle of the board, which is where the point of maximum deflection is 0.047 inches. Okay, next problem. This is number 4 on page 88. What is the uniform load that will cause that same shelf, Eastern White Pine, same flexural modulus, what will cause that to deflect 1/2 inch, assuming the stress remains in the elastic region? So we're told to assume it remains in the elastic region. That's wonderful, because now we don't have to check the value of stress and make sure that it remains below the flexural yield stress. All right, so we're assuming it remains in the elastic region. That's wonderful. And we're given the dimensions and the span of the beam. All right, so what's going to cause it to deflect 1/2 inch? So now this is really very similar to the last problem, but now we're trying to find the force, or ultimately the uniform load W, that will result in a deflection of 1/2 inch. So now we're going to go ahead and plug in, for delta max, we're going to plug in 1/2 inch, and we'll find the resulting F. And then once we know F, we'll use F equals WL to find the uniform load in pounds force per feet. So that's what we're going to do. But we're going to need the moment of inertia, right? So we solve for the moment of inertia, and then we can solve for F, because we're asked what's it going to take to get this to deflect by 1/2 inch. So that's 1/2 inch, and we'll solve for moment of inertia, and then we'll solve for F. And once we have F, then we'll use this equation to solve for the uniformly distributed load, W. So that's our plan. Got to find the moment of inertia first. This is the exact same as in problem number 3, the previous problem. So it's still 0.1406 inches to the fourth. And now I want to rearrange this equation to solve for F. So divide both sides by 5L cubed, multiply both sides times 384 E sub B times I, and this is what you end up with. And now you can plug in all these numbers because we know all of these. So there's part of the constant, 384. There's the flexural modulus, which was given. There's the moment of inertia that we calculated. There is delta max. So we're trying to solve for the force when the deflection is 0.5 inches. And down here we have 5. That's from part of the constant. And here is L cubed. Once again, make sure that you're plugging this in the right units, because the rest of this equation has inches. We're plugging the deflection in terms of inches, and we have PSI right here for the flexural modulus. So this has to be in inches to get these units to cancel out. So once I plug all these numbers into my calculator and I cancel out the units, I'll be left with 531 pounds force. That's the total force on the beam, but it's a uniformly distributed load, and that load is distributed over 2 feet. Or here, here you could say 24 inches. It didn't tell us what units to put the uniform load in, so if your answer is in pounds force per inch, that's fine. It'll just be 12 times less than that. All right, so W equals F divided by L. So there's our F. Here's our L in feet, but you could put in 24 inches here, and that would be fine. And so here you get 265.5 pounds force per foot. Or you could convert that to inches, and that would be correct too, because it doesn't matter here whether our answer is in pounds force per foot or pounds force per inch. Either one would be correct here. So you can convert that to inches if you wanted to. Okay, last problem on page 88. We have that same shelf made of eastern white pine, and we're given the flexural strength now and the dimensions, and we want to know what is the uniform load W that will cause this to fail, will cause it to break. All right, so what's our strategy here? Well, we know the flexural strength, and that is a value of stress. So we're going to have to use our stress equation and plug in the flexural strength into the parameter for stress, and then we're going to have to solve for F, the force. And once we have the force, then we can convert to the uniform load W, just like we did in the previous problem. All right, and in the process, we're going to need the moment of inertia as well, which we've already got. Okay, so let's do that. Here is our equation for stress in a simply supported beam with a uniform load applied to it. How do I know that we need to use the stress equation instead of the deflection equation? Well, we're trying to use the flexural strength, right? The modulus of rupture, and that is the stress when it fails. And so we need to use the stress equation so we can plug in the flexural strength, or the modulus of rupture, same thing, to this value right here. So what do we have to do? We have to find I, which we already had from the previous problems. It's the same geometry. And then we're going to solve for F. And once we know F, we're going to use F equals WL to solve for W, which is the uniform load. All right, so let's do that. Here's the moments of inertia. It's the same thing as it was in the previous two problems. The geometry hasn't changed. So we still have a moment of inertia of 0.1406 inches to the fourth. And this is our stress equation for a simply supported beam with a uniform load. I want to rearrange this equation and solve for F to find how much force does it take to reach the flexural strength for the stress value. So I'm going to multiply both sides times 16I and divide both sides by by LH. I'm going to leave F there. And when I do that, I get this equation. And I know all these things, so I can plug in. 16 is from the constant. This is our moment of inertia. This is our stress value, which is the flexural strength. And this is L. Once again, got to put it in terms of inches so that I get units to cancel out. And H is the height of the beam, and we were given that the height of the beam is 3/4 of an inch or 0.75 inches. So plug these into your calculator, cancel out your units, and you'll find that the force required to reach that stress level is 1,187.3 pounds force. But once again, that's the total force, and we want to know what is the uniformly applied load. So use this equation, solve for W, and plug in your value for F and for L. Once again, if you wanted to, you could plug in 24 inches right here. That would be fine because it didn't tell us what units to use for the uniformly distributed load. So pounds force per foot is fine, or pounds force per inch is fine. So I divided by 2 feet, and I got 593.6 pounds force per foot. And this is the uniform load that is just enough to cause the beam to reach a stress that is equal to the flexural strength, which will cause the beam to fail. So the beam's going to break if I apply this amount of uniform load to the beam. All right, I think I'll call that good for video 1. So we just went over all of the example problems on page 87 and 88. And just to break things up, I think I'll make a second video to go over the example problems on page 89. So I'm going to stop this video here. I'll see you in the next video where we will review problem set number 2.